Problem 7a. I might have answered this already in the first video, but let's do it again anyway. The number of points, over f to q to the rth is q to the rth to mth power and now I forget. Yeah, I have to write it up, the definition. I think we have had that. Oh yeah, that was the result of of problem 2, I think. So I'll just look it up. There's no need to make it more complicated. So it was just the power of where alpha is q to nth or to mth. So it's 1 minus q to the mth t. B, the projective space over fq, write it as disjoint union of the affine spaces. We probably had this before, but it's the affine space and then the disjoint union with the space at infinity, which is the projective space over K of dimension 1 minus 1. So by induction we get the disjoint union and then when I is naught, it's just a point. So it's from I equals naught up to m. So we need to have the number of points is the sum of these, so the z function will be the product of these, where instead of m we sum over I. Next we have to verify this, counting equivalent classes of intervals. So how many intervals do we have? That is m tuples of the affine space. So there are each of them have q to rth. So we are in the affine space over f q to rth. So each number in the m plus 1 tuple can have q minus r possibilities. So that must be n raised to m plus 1. Then we have all the tuples, and we need to subtract the null tuple. So that's the number of tuples. And the equivalence class, they are equal if they are multiplied by a number in fq to the rth not being naught. So that's the number of, and then we can perform the division and get the sum of q to the rth to power I for I equals naught to m. And that's exactly what we used up here. So lucky. That was another quickie.